Hi AP Calc gang. As we start our second quarter here, actually fourth quarter, we're going to start with lesson 6.1, and we're going to split this up into a couple parts. So first of all, we're going to talk about the indefinite integral, and then tomorrow we'll talk a little bit more, or tonight actually you'll see some more stuff about something weird called slope fields, and then also something called initial value problems. Anyway, today though we're going to talk about indefinite integral, and as you look at these things you probably notice something a little bit different about this integral as opposed to the other ones, namely that we call these indefinite integrals. There's no upper or lower bounds on these. Up to this point, that's what we've been seeing, a particular numbers here and here, or particular, or perhaps variables, but here we have nothing. But we have seen in last chapter that one way to evaluate integrals is with that fundamental theorem of calculus, which is using antiderivatives, symbolized by this capital F, And the other thing that's a little bit different here is this plus c, and that's just a general representation for any constant. Because we have an indefinite integral, we can't figure out exactly what the integral is. We can figure out the majority of it using this antiderivative, but this constant here is something that I'm not real sure ever what it is, but I need to have that c there that would take into account all different kinds of constants that would work here. All right, well, let's look at a couple examples. Alright, so here's 3 examples here. Let's take a look at these. First one, x to the 4th dx. Again, when we take antiderivatives of that, we're looking for a bigger power. And so it is going to be, just a second here, I'm going to thicken my pen here a bit. We're going to have x to the 5th, but then as we imagine taking the derivative of this, it would be 5 times x to the 4th, but there's no 5 in the problem. And so then we have to account for that by multiplying by 1/5 like that. And again, don't forget that to finish out this problem I need to put plus c in there, such as that. Alright, let's take the next one. Now the next one we might recall that it's a lot of times better to write the square root as x to the 1/2 power. And so now when I take the antiderivative of that, again I'm looking for a bigger power. So 1 bigger than 1/2 is 1 1/2, or we would typically write that as x to the 3/2. But again, my original problem did not have any coefficient, didn't have anything in front of x. So when I multiply, when I use the product rule to find the derivative of x to the 3/2, I better have a 2/3 out here in front. And then I believe it will work out. And once again, I tack on that plus c there. Lastly, last one here, here's one of our trig derivatives. We remember that the derivative of sine is cosine, so thinking antiderivative-wise, it's probably going to be the sine of 2x. But if I did the derivative of the sine of 2x, yeah, it would be the cosine of 2x times 2. And again, I don't have that times 2 out in front, so in order to account for that, I'm going to put this 1/2 out in front. So there's some basic examples of how we're using, oops, what did I forget, class? The plus c at the end here. I almost forgot that. I guarantee that in a test or a quiz or something, you guys are going to forget that plus c, and then you will bang your head against the table when you do that, but that's okay. Alright, here's some basic properties of indefinite integrals. You have these in your book. This might be kind of difficult to see, I think. I just wanted to point out a couple of them. If we ever have some things added, the integral of more than one term like that, basically you can separate each particular term and take the integral of each one. We'll take a look at an example of that here in a second. Here's another common one, this number 3. If you have some number times that function, you can pull that number out in front of the integral. It doesn't make any difference at all what the integral is, and sometimes that makes things a little bit easier. Here's some other ones that you can take a look at. Again, it might be a little bit easier to see in your book. These are good ones to write down. There are some of these on your spark chart, not all of them, but I would say the most essential ones to remember are this one, number 2, and also this one, number 3. Those are the ones that we'll be using a lot as we move throughout this chapter and beyond. All right, let's just see how this works in action here when we have the integral of several terms like this. Basically what that means is I can separate it out and take the integral of each one separately. So I'll just write it like this. And again, it would be a dx by each one of those. I won't bother to write that in there. Now let's just do each of these separately. Now again, when you think about the antiderivative of e to the 2x, it's going to be the same thing. However, remember I would be, if I took the derivative of this, I'd be multiplying by 2, and so I better find some way to cancel out that 2 in front of this then. So 1/2 e to the 2x is what we'll get there. This middle one is fairly easy because I know my bigger power is going to be x to the 3rd, and in this case there is a 3 there. Notice when I take the derivative of x to the 3rd is 3x squared, so I don't have to do anything with that. And then finally, this 1 over x is kind of strange. Oftentimes you might say, well, could I write that as x to the -1 power? And you could, but then remember 1 power bigger than -1 is 0, so that looks a little fishy. But it's good to remember what function is associated with 1 over x. And I think some of you already have that by now. It is that natural log function, so ln of x. The derivative of this ln of x is 1 over x. So there's my derivative there, and do not forget old reliable plus c, always needed with these indefinite integrals. Alright, thanks for watching, and now we can begin to work on this first set of problems from lesson 6.1.